good day, everybody. It's my pleasure to be presenting today our it's going to be a mixture of compressed air, ambient air, and gas purification webinar. And just a brief introduction to John Brooks. We're a multifaceted company consisting of pumps, spray nozzles, valves, and my domain is the filtration aspect. And in association with all these products, we also provide technical webinars to enlighten our customers of technology and different operating parameters for filtration, pumps, and various products that we represent. Today, I have the pleasure of having as my co-host or my participant, Henk. He's from the manufacturer Dollinger, and he'll be assisting me in the technical aspects of this presentation. We also have our panelists, Anita and Nico. Anita is Canadian sales manager for the filtration group of John Brooks, and Nico is sales supervisor for also, I guess, Canada, inside sales supervisor. And they'll be our panelists. At the bottom of your screen, you should see a question icon, which you can input your questions, and the panelists will forward them to me or ask me at the end of the presentation. So to get the show on the road, today's presentation, again, it's consisting of compressed air, ambient air, and gas purification. John Brooks, family-owned company, founded in 1938, consists of approximately 200 plus employees, privately owned. And as previously stated, we're a multifaceted company. We consist of spray nozzles, pumps, filtration, valves. We have a ASME-approved fabrication shop, so we can custom make pressure vessels, filtration skids, basically anything that an ASME-approved facility would require. And we also represent heat exchangers, purification systems, and gas purification equipment. A quick recap of the previous presentation consisted of compressed air, capacity versus pressure. It was mainly the energy costs associated with fabricating compressed air as utility, the cost of once you compress the air, then if you have a leak, there's a cost associated to that. Compressed air filtration costs, depending on the type of filtration that you do. Is it just simple particle removal, liquid removal, dehydration? So the capital or the operating costs go up dependent on the level of filtration required. So that was a previous recap, which you can access the webinars through our John Brooks site, and just feel free to contact us and we'll give you the links, or you can always go on YouTube. Just to summarize, today's presentation consists of air intake filters, oil mist eliminators, I'm not going to be covering liquid filtration, that one slipped in there, compressed gas filtration, and at the end we'll have a few moments to answer any of your questions. Typically, when we talk about filtration, there's multiple methods of filtering air, gas, and typically it would consist of, using a pleated filter media. We can use centrifugal forces, which I'll elaborate a bit more on, to remove larger particles. So it's always dependent on the level of filtration that the client needs. And the goal is always to not filter to a finer micron or specification than required, because the associated cost of pressure drop, the longevity of the filter, would have a negative impact if you're filtering down to a smaller level than actually is required. And when we talk about filtration, there's multiple methods of evaluating the level of filtration you require. And in most industries, the two terms used are absolute filtration, meaning that it would be approximately 100% particulate removal, and then there's nominal rating. So nominal rating can be from 98%, 95%. So whenever they claim that it's a nominal rating, it would be almost recommended to find out what is the percentage of that nominal rating. Hank, you were indicating at one time that, you know, it's almost impossible to get an absolute rated filter, but, you know, we try to get as close as possible to that rating to assure that it complies with the customer requirements.
Yeah, that's correct. If you want, for example, 2 micron, 99 over 100% of 2 micron, then you don't look at a 99, but you're looking at a 98% of 0.3 micron. Then you have to look at the filter material. But then you come to the nominal rating of the filter media. What is that filter media capable to? So, that we have test filter media that we've run several times and on a single pass, and that's what we base our nominal rating on as 2 micron, 98% of 2 micron, 98% of 10 micron, depending on what the customer needs.
Okay. Thank you. Good point. And so we'll start with our ambient air intake particulate filtration. And it can be as simple as, you know, a cartridge filter where we're just trying to take particulates out, as illustrated on the left-hand side of your screen. And then it could get to as elaborated or as large scale as a, you know, a gas compression station where they're fabricating either oxygen, nitrogen, or some gases from ambient air, and they're extracting nitrogen or oxygen, or even, you know, other gases that are existent in ambient air. As illustrated on the right-hand side, this would be a large volume gas compression station. Ideally, you know, we like to have nice clean air entering these intake filters. In reality, these intake filters are commonly installed in corrosive plants. It could be dust-laden facilities. It could be in the desert where there's sandstorms. Basically, they can be installed anywhere. So on the right-hand side, you see some of the louvers to prevent rain, snow, other particulates that are falling from the sky from getting introduced into the air intakes. And typically, which we'll elaborate a bit more on, they are installed at a certain elevation so the ground dust does not get introduced into the air intake. So we like to have it at a certain elevation, which we'll elaborate a bit more on later. Regretfully, not all of the installations that we have to install equipment in are nice, clean installations. And I call this one air intakes with an issue. And basically, you know, what some of the issues that we can have in Canadian or Northern American climates is that frost buildup could build up at the air intake. If you have a certain velocity, a certain moisture content in the ambient air, basically you'll block up the air intakes due to frost accumulation. So some of the technologies we use to prevent that is we'd even put electrical heaters just prior to the air intake to assure that sufficient heat is supplied to prevent frost buildup. Another method is using the hot oil or hot gas from the compressor to recirculate through tubes just prior to the air intake to heat up the air partially to prevent that frost buildup. And happily, once the air gets so cold, there is so minimal amount of moisture in the ambient air that below something like, you know, minus 10 degrees Celsius or so, we shut the heaters off because there's almost minimal moisture content in the ambient air. And so we don't need that no more. The middle of the slide is just showing again the louvers that we install to prevent snow, rain, just ambient conditions from getting introduced into the air intake. And then in certain circumstances, we install our air intakes in facilities where they can have certain chemical contaminations. Could be acid or different, you know, negative chemicals that we don't want to introduce into our air intakes, which would corrode the propellers on the compressors, on gas compression equipment, So the goal is always to eliminate the contaminants as early as possible so they don't create any negative consequences downstream once the gas or air gets compressed. And the purple pinkish desiccant that you see there is basically a scrubber that removes acid contamination. So that would be a first stage prior to the filtration, and we would assure that none of those particulates from the desiccant material go downstream. Hank, anything you want to elaborate on these air intakes with issues, or we're good to go?
No, I got nothing to add to it at this point.
Hey,
Intakes.
Sounds good. On the next one, basically we're looking at a first stage of filtration. So as previously stated, you know, filter elements create a pressure drop. They have a certain cost to change the elements out. The company that Hank works for, they basically developed a centrifugal method of eliminating all particulates 15 micron and larger, or 98% of them, and it also at the same time removes moisture or liquid droplets in 99.4% of all moisture. And basically the simple principle of operation is the air velocity is caused to create like a spin action or a centrifugal action, and it sends to the outer parameters of the filter element the larger particles, and then they get dropped out and are dropped out to atmosphere. And then the interesting point that Hank clarified to me is that, you know, we may have 100% of the air coming in, but then there is a certain loss of air that is expelled to the atmosphere, and another percentage or the majority would be going to the air intake, which is the clean air. And this is to knock out the larger particles, prolong the life of the second stage filtration. And Hank, can you elaborate, like, what is the approximate loss of air? You know, if we have 100% coming in and then we have a certain percent coming out, so there is is it a 5-10% that we have to oversize these elements on?
It's about 10%. It's about
Okay.
10% that you will lose. So from for the flow rate you need to get through your filter elements, you need to take 110% of that. So times 1.1 to size the surface for these spin filters. And it will require a blower to remove that air from it. Otherwise, you'll get kind of a pressure buildup. You want it under pressure. So this spin filter system will require a secondary blower to remove that 10% air.
Yeah. And I've seen these spin filters used in dusty mine conditions where they purposely spray a mist of water prior to the air intakes. And it's just a method of the water mist conglomerating with the particles to create a certain mass. So this way it efficiently removes the moisture, or not the moisture, but the particulate from the intake airstream. And it's a cost-efficient method of basically cleaning your air.
Yeah, and we've used these in trains, in different locations, not just mines, but where a lot of dust is, in deserts. We'll use them there as the first stage, or sometimes just one. It's what we call a dense pack. It's the spin filter and then a 10 micron panel, or we'll do a 2 or a 0.3 micron panel.
Hey, talking about those panels, that's the next slide. So here we see some of the panels that are downstream of the spin filters. So basically this would be the second stage of filtration. The third slide would be similarly the second stage of filtration. And one of these 24-inch by 24-inch panels, they can handle approximately 3,000 SCFM, which is more than many of our competitors. So we can create a smaller. Yes?
Senna, sorry, I need to correct you. The 24 by 24, we have the 517 and the 518 can do about 2500 CFM. The
Yeah.
519 can about 2000. And then we have the new generation panel, the first stage and the second stage. They can do the 3000 CFM, and then the 0.3 micron panel can do 2500 CFM.
Correct. Yeah. So
Yep.
goes with the rule of thought that, you know, the finer that you filter it down, then it has either a higher pressure drop or reduces the capacity of the filter element. Good point, Hank. And illustrated just below, we see a different design of air intake filtration. And basically this is a pulse jet system. And you see the various tubing which would supply compressed air to clean out the element, which is the one illustrated, the oval, or not oval, the slanted element here. Basically, the method of operation is that the airstream goes from the outside towards the inside. When there's a certain pressure drop, it automatically sends a pulse of air to backfeed this element, cleaning out the element. And I think we have a better illustration of that on the following slide. Yeah, here you see a number of these elements. This is a pulse jet system, and they don't all pulse at the same time because we don't want to have an interrupted flow of air. So it would be, you know, one of the two would be pulsing when required, and it would continue pulsing until the elements have lowered their pressure drop to an acceptable level that we can put them back in operation. Let's see if we can illustrate this better here. No. There she is. So this is just a slow motion showing accumulated dust that would be blown off when the pulse takes place, and it self-cleans the element. The accumulated dirt drops to the bottom. This unit is typically installed approximately 10 above ground level, and then the dirt would just drop to the bottom or to ground level. That would have to be cleaned out on a regular basis. So it's sort of nice to see, you know, some of these units in operation, but, you know, what's the goal of why do we want to clean the air prior to compressed air intakes, gas generators? And it all falls down to, you know, we want to keep the compressor performance at its optimal levels. We want to increase the compressor life. So we don't want to have particulate eroding the internals of a compressor. You know, by filtering particles out at a preliminary stage, it reduces maintenance, repair, downtime. So it just increases the reliability of your equipment. And then key factor is you don't want to have process or product contamination. So depending on the application the air is used for, you want to get as much or all the contaminants out, being chemical contaminants, particulate contaminants. You know, we even filter for shad flies in different seasons of the year, depending on the locations of installation. So the cleaner, the better you filter at the initial stage, the less troubles you have downstream. And then there's certain rule of thumbs that initially, you know, for a blower, we would indicate a 10 micron filtration level would be sufficient. Similarly for a reciprocating compressor or for a screw compressor. For centrifugal and turbine compressors or equipment, you know, we would go down to a finer micron level from 2 to 3 micron. But we always request from the customer what is the optimal level of filtration for their needs, because we don't want to over filter and create higher pressure drop or increase the capital cost. So it's made on design basis based on the requirements of the actual application. Some basic installation guidelines, as I illustrated earlier, is that, you know, we want to have the air intakes approximately 10 feet or higher above ground level. Install it at least 6 feet from walls, roofs, any other sources and contaminants. Just we're trying to stay away as far as possible from any source of contaminants, as indicated in line item number 3. We don't want to have, you know, vapors coming out of a facility that'll just get sucked in by your air intakes, or there could be oil mist or other negative gases coming out of a facility. So we want to be as far as possible from any sources of contaminants. You know, we consider prevailing winds. We don't want to take air from a room, because then the amount of BTUs or the heat required to reheat that room would be not cost effective. And we want to minimize pipe lengths and bends. Pipe lengths create pressure drop, bends create pressure drop. So we want to always keep to a minimum bends and the length of the pipes, have it as close to the point of use as possible. And then we have to have accommodations so that the personnel can change out the filters or have some method of maintaining this equipment. Hank, do you think that pretty much covers? Anything else you'd like to add on the air intakes?
No, so far it's like we've discussed before. It's everything needs to be provided by the customers to properly size it, to make sure that we don't oversize it or undersize it, and we can add a silencer to it if needed, to reduce any noises that coming from the blower. But other than that, nope, pretty good.
Good point. I forgot about the silencers, and that is definitely a source of noise. Some of these air intakes, even though it is sucking the air in, it still is a substantial source of noise. Yeah. Hey, the next section we're going to be getting to is, you know, some of the contaminants that facilities create, and we want to assure that oil vapors, this is basically going to be consisting of oil vapors that are exiting from process plants, from gas generating plants. And one of the reasons we want to eliminate these oil mists is so they don't get sucked in by the air intake filters that we previously discussed. And here we're just illustrating some of the oil mist that is created from gear lubrication, equipment that is spinning at high velocities, that have bearings and that have oil for cooling purposes, lubrication purposes. And there is a certain oil mist that is created, which commonly presently gets emitted to the atmosphere. So John Brooks, being an environmental company, we always try to do what is best for the environment and you know, minimize oil vapors going into the atmosphere. And here we're just illustrating some of the little vapors that come out of different crankcases, gear lubricators, and it's just in a vapor form. And typically these vapors are in approximately, you know, 0.3 micron in size. And we'll illustrate or elaborate a bit more on that aspect. So why do we want to control oil mist emissions? You know, I'll start with the environmental one. That's the easy one. Basically, you know, from an environmental standpoint, we want to keep our air clean, you know, keep this planet going, sort of thing. From an economic standpoint, if you were flowing approximately 200 CFM of oil mist consisting of 100 ppm of oil, that would equate to approximately 100 gallons over a span of a year. So just the economics of, you know, wasting that 100 gallons when it could be recuperated and sent back into the crankcase or the location where this oil mist is originally coming from. And typically the oil even comes back cleaner than it's emitted because it goes through a filter and then is subject back to the crankcase. And always from a safety standpoint, if you have oil mists exiting a facility, then that would be a safety hazard because it could go on walkways, ladders, different locations where it can cause a slippery condition. And so there's the safety aspect of it. Basically, there's 3 different designs for oil mist eliminators. And the simple one is when there's a positive pressure from the source and it overcomes the differential pressure of the element. So the differential pressure is quite low on these. It's only 18 inches water column. So if there's a positive pressure in the crankcase, it'll just flow that oil mist through the coalescing element and basically goes out to atmosphere. And then it's not illustrated here, but there would be a drip line at the base of this housing, which would feed the condensed or the coalesced oil back into your crankcase so you can recuperate that oil. Or if you want to recuperate it, if it's contaminated with other liquids, if there's water contamination, then that can be sent to a disposal drum, which could be disposed of at a later time. So that's with positive pressure. Certain crankcases don't have a positive pressure. So we have our oil mist flow, which would be coming in from the right, and then we subject it to compressed, or we install basically a venturi on here, which creates a vacuum, and the compressed air flowing through the venturi creates a vacuum. So it basically sucks in the oil vapors, assisting in the elimination of the oil vapors. So this is for small flows up to approximately 60 SCFM, and very cost effective. Just need a little compressed air line to feed some air and does the trick excellently. For larger scale installations, we actually install a pump, and it would be similarly to like a vacuum blower that would assist in creating that vacuum and create a negative pressure. So in the crankcase, there is a negative pressure and it extracts the oil vapors from the crankcase. What's the cause of oil mist? As previously stated, oil mist is from crankcases. It's from oil that is in contact with bearings that reach temperatures between 350 and 700 degrees Fahrenheit on rotating equipment. And these machines typically use large volumes of oil for cooling purposes, for lubrication purposes, and consequence of these high temperatures, the rotating equipment, the shear factor causes oil vapors to be created. And as previously stated, the oil vapors are, it's a very fine oil mist. So it is a condensed mist. So it's not in a vapor form, but it would be like in an aerosol form. So how do we eliminate this oil mist from the exhaust of these pipes or from the source? Most simple method to do it is to coalesce it. So we start off with very fine liquid droplets, and coalesce is just basically taking small droplets, putting them together with other small droplets to make larger droplets. And once they get large enough that due to gravity, they have sufficient mass that they can be eliminated by the outer parameter of the filter element. And that's pretty much the summary of a coalescer. Okay. Hey, Hank, what do you think? Does that summarize coalescing principle?
Yep. Yeah,
okay.
Perfect. I can add anything else.
Thanks, Hank. So here's a sample of one of our coalescing filter housings, and the flow of the gas is always from the inside out, basically coming in on the right-hand side, coming out at the left-hand side. And the reason it has to be inside out is because there would be a drain line or a drain valve located at the sump area to eliminate the coalesced or accumulated liquids that we want to eliminate. And these coalescing filters could be used for oils, water, basically removing any liquids or mists out of a air line, compressed natural gas line. It could be CO2 lines that have a certain water mist in it, and it's just to minimize the water quantity or liquid quantity in a gas compressed air line. Yeah. Well, in a sense, I skipped over a point there because I transitioned from the oil mist eliminator to the coalescing filters, Hank. But it's the same process, except this is coalescing filters are used more for gas lines compared to the oil mist eliminators are used on crankcases. Same concept is that in a compressed gas line, we would be still coalescing the little aerosols into larger liquid droplets. And again, due to gravity, they would be eliminated by the outer drainage layer of these filter elements. So since these are used in compressed air lines, they would typically have approximately, Hank, maybe you can clarify this one. What would be the typical pressure drop that these filter elements can withstand?
It's usually for oil mist eliminators, we advise 30 inches of water column. I believe that for the gas filter, for the coalescing pipeline filters, it's pretty much the same pressure drop. Might be a little bit higher, but not by much.
Yeah. So these have an inner core just to structurally make it stronger, and in the chance that there's a reverse flow, it would prevent the element from collapsing. But as previously stated, these elements, the flow of the gas is always from inside out. So inner support core, then you have your filter media, that is the coalescing aspect of it, and then you have a drainage layer. And what we find interesting when we service some of these filter elements, we notice that at the lower quadrant of this element, the element seems to be dirty. And that is part of the design, that we want the droplets to be dropping off at the lower quadrant of the filter element. If they were coming off at the top, then the air velocity or the gas velocity is higher, so you can have reentrainment of those droplets as it's going through the filter housing. I'll just go back here, and basically we see them get stained at the lower quadrant of the filter elements. And our goal is always that the droplets come out at the bottom. If they were coming out at the top, then there's more velocity, so there's more chance that those droplets would get reentrained and go out. So when our customers tell me that, you know, hey, your element only looks half used because it's only half stained, that's part of the design, and we want the droplets to be coming out at the lower quadrant of the filter element. Here we have an illustration of fuel gas conditioning skid, and it uses in this design multiple methods of filtration. So we're using gravity, separation, coalescing, and I'll just let the illustration show a bit of the design. So this would be a two parallel system, two filtration skids in parallel. And the first stage of filtration is solely using gravity and perhaps like a mesh pad. So we have the compressed gas coming in, going through the first stage. So this would remove the bulk liquids. By removing the bulk liquids, we're pre-filtering the gas and minimizing the contamination load on the second stage. The second stage is more of a coalescing filter, So it is more efficient, removes more of the finer oil mists, but it is a consumable item at the second stage. So the finer we can filter at the first stage, the lower the operating cost is for the second stage, the lower the pressure drop is, because you're not trying to remove all the contaminants through a filtration equipment. The next section I'm going to be talking about is about particulate filters. So particulate filters, design-wise, similar to the coalescing filters, except we're not removing any mists, liquids, droplets. It's not a liquid filtration, or it's not a method of removing liquids from a gas. These are solely designed for particulate removal. So if you already have a clean, dry gas, particulate filters are the way to go. And one of the reasons I mentioned that is because you have typically a larger filtration area with a particulate filter for the same size of housing. The logic behind that is on particulate filters, we would be filtering from the outside in to take advantage of that larger surface area. For coalescing filters, we have no choice but to go from inside out because of the accumulated liquid that we have to drain. So this slide illustrates basically our particulate filter with depleted media. The media could consist of, multiple materials to accommodate the corrosive gases or the micron levels. So I think there's approximately, I don't know, would you say 200 different materials and configurations that we have for filtration?
I know that we have a large number of different sizes. We have about 20 to 25 filter medias that we use on a regular base, and then we also do stainless steel, cast alloy, for very, very corrosive, and where very clean filters are required. So if the filter cannot the little parts from the filter media like glass fiber,
Yeah.
if that cannot be in the process, and then we can go to a stainless steel media. You see it in looking for the term OxyClean service. We nowadays go to even to a stainless steel element.
Okay. And these would vary anywhere from, like, I know for natural gas, we typically go approximately 10 micron filtration, but, I think we go from approximately 1 micron to, I don't know what the limit is from a core standpoint, but, there's a multitude of filter elements to suit each customer needs. If it's for removal of desiccant dust, we would have particulate filters. If it's for rust scale in a natural gas pipeline, we would have, that would be typically approximately 10 micron. But then it's also sized based on the application. So if we know if it's for natural gas and they have nozzles downstream, perhaps we would recommend that the filtration level is approximately 1/3 of the nozzle side or 1/4, based on the requirement for the gas or compressed air. Then there's certain criteria we take into consideration when we make the filter elements, when we make the filter housings. And, if I can just put in a little plug, John Brooks, we own a company called MDA. So we fabricate our own pressure vessels. So we have a ASME approved facility. So we can make custom designed filter housings, and we work in association or hand in hand with Henk, which is one of the design engineers, to create or fabricate custom-made filter housing. So this way we minimize the customer's requirements for pipe changes. If they have an existing filter housing that they want to change, we can accommodate that and make it to the customer's needs. But just to go back to the filter elements, some of these filters operated at pressures from 100 psi to 1,000 psi. So we have to accommodate differential pressures or collapse pressures of these elements to assure that if they have 1,000 or 800 psi line and somebody's opening up a valve instantaneously, then there's like almost a hammer effect. So we want to assure that the filter element is constructed strong enough to accommodate, large differential pressures. No longer than, I'd say, a year ago, we had a customer that bought a retrofit element that only had a 10 psi differential pressure maximum. And within less than a year, the filter collapsed, and then all that particulate and dirt that they were trying to prevent from going downstream just ended up going downstream. And the whole goal of removing the particulate from your compressed gas line was eliminated, because now you just contaminated all your infrastructure with that particulate. Always the filter housing, we always like to have a large sump area just to take advantage of gravity to knock out some of the particulates. So it could be for liquids, particulates. If we slow down the velocity of the gas or air, then some of the larger particulates will just naturally drop off. And then, as previously stated, like, we build custom filter housings to accommodate the customer's needs.
Is that it?
Yeah.
Yeah. No. Oh, go ahead. We'll finish. I'll tell what I wanted to say at this one.
Yeah. So I'll keep going then. Okay.
Yep.
And as I stated earlier, the filter elements have an inner support screen. So for particulate filters, the flow of the gas or air is from outside in. Typically, the collapse pressure is 25 to 50 psi. We go up to also 100 psi in certain circumstances. They would weld like inner support cores inside and just make it structurally stronger. Then we have to place I guess you'd call it a wire mesh or some sort of support to put the media on. And we want to have as much media as possible. So this way the life of the filter element is as long as possible, the pressure drop as long as possible. So we create a, sort of like a fin type extrusion that the media would be applied to. And even in certain circumstances, we have customers, if they have, or if they're filtering materials that are of certain value, we strip the media off, send it back. We had a facility that used these filters for platinum extraction, and they would take the media off, basically burn it and recuperate the platinum because of the value of the metal. Is there something you want to add on this one, Henk?
Yeah. So we have a lot of standard elements, but we have a number of companies where we change or modify. Like you said, we can go collapse pressure, we can increase the collapse pressure, but we can modify our designs to fit the customer needs. Recently, I have for a large company a vacuum filter, and they had some issues with installing it and in the housing that they already had. They were looking for an element. We can build an element without any additional charges, no special charges. It will be based on our regular rates, a filter element for that housing for that customer.
Yeah. So good point. As similarly, I stated earlier, we can make custom housings. We can also make custom elements to fit into competitive units. And we can modify the micron rating based on the needs of the customer. So even if they had a previous installation where they thought, 20 micron was sufficient, we can modify the element and supply something that would be finer or coarser as the requirements require. Then, when we design these filters, there's multiple factors that have to be taken into consideration. Some of the basic ones are the inlet pressure, the pressure drop, the flow rate. So in previous webinars, I always explained that the worst operating conditions for gas filtration is the lowest pressure and the highest velocity. And as illustrated on this slide, we see that 4-inch filter housing, if it's operating at 150 psi and you want to respect a quarter or 0.25 psi pressure drop at 150 psi, this filter housings would only have a capacity of 2,100 SCFM. If you were operating the same filter housing but at 275 psi, we're compressing that gas at the higher pressure. So now the capacity of that filter housing would increase to 2,750 psi. One of the reasons I'm sort of elaborating on this topic is because it is important these filter housings can operate at 800 psi, and at 800 psi then we have to assure that the differential pressure is low enough so we're not approaching anywhere close to the collapse pressure. We want to minimize pressure drop to assure energy efficiency. You just spend X amount of money to compress the gas or the air to a certain pressure, and now we're restricting it by having a filter element that is, yes, eliminating the particles, but it's also reducing the pressure that you need downstream. And as I stated, if you can accommodate a higher pressure drop, then the same filter housing can handle approximately 9,400 SCFM. So that's a radical difference, from 9,400 to 2,100. Again, just taking into consideration the operating pressure, and then also, I guess it would be the specific gravity of the gas would also have a consequence on the capacity of the filter housing, because natural gas is a lighter gas, or so there's typically like a 0.6 coefficient that we use when calculating the pressure drop because of the gas is natural gas. Hey, Henk, you're usually the expert on natural gas applications. Anything you want to add to that one?
Well, just that sizing a housing is a delicate balance between the operating area that you have. You're talking about the 3 psi. This is the 3 psi clean. This means that if the vessel is installed in the pipeline and you open up the valve, then you'll see 3 psi. Well, we advise to remove the elements at about 8 psi. We do that because of the security, because if you leave it to people and say, oh, we can do it to 25 psi, we've had situations where customers have let the pressure drop over the element go way up over, and they had one shockwave going through their system and the element imploded in the housing. And that's why we strongly recommend remove it at 8 psi. But if you have 3 psi to start with, then you have a working differential of 5 psi. If you have a low application, then you don't want a high pressure drop. If you have a high pressure, then you can get away with a high pressure drop, but you just need to be mindful of that difference. And the biggest influence on the pressure drop is not the element, it is the connection size. The connection size, we see applications where customers say, oh, we want a 4-inch housing, and they'll have a 6 psi pressure drop clean. And we advise them to go with a bigger nozzle. The biggest influence on the pressure drop is the nozzle size. I've seen applications where the customer says 4, we advise 6 and sometimes even 8 or 10-inch connections, so that the initial pressure drop is within an acceptable range. So it's a fine balance between the right connection sizes, the speed, the flow, the speed that the gas has entering into the element, the filter housing is very important. The speed through the velocity through the media is very important. So these are all things that we consider in sizing that housing.
That's a good point, Hank. You know, it makes me just think that this is almost like a science, you know, so I guess it depends on the pressure, the dirt load, you know, so you can modify the nozzle size or the inlet outlet connections. You can change the diameter of the actual vessel that's holding that filter element based on the customer's needs. And
Correct.
it's not as simple as, you know, just sort of saying, hey, I got a 4-inch line. I have a certain micron level and we're off to the races. You know, this is more of a science, and you know, that's why we have you on board, Hank, to help us out on these kind of applications.
Glad to be on board.
Thanks. So that pretty much summarizes our presentation for today. If there's any questions that you've submitted to our panelists, we'd be more than happy to reply to them. As previously I stated, you can always access our website where you can see previously recorded webinars. We've done them on filtration, liquid filtration, pumps of various designs, self-metering, liquid filtration, self-cleaning, and it's also a method for us to reply to any additional questions you may have. You know, if you can reach out to myself, some of our panelists, I have all my colleagues across Canada that would be more than happy to reply to your questions.
So
we do have a few questions. Oh, okay. Sorry, Anita, do you want to bring them up?
No, go ahead, Nico, please.
Yep. Okay, one of the first questions is, would spin filters work in an environment where there is cement or clay and wet particulate, which can stick to the spin filters?
Yes, it could work. But we'll have to investigate that to make sure that it doesn't stick. We have applications in cement factories where it works really good. Sometimes you'll have to clean them manually, but will depend on how dirty the air is.
Yeah. And hey, Hank, just bringing up the topic of spin filters in the cement application, interesting one. What would the spin filters they're made out of? It's a certain plastic, nylon. Just, you know, figure we may answer this question in more detail by, you know, letting them know if we can hose these down after, because they definitely are made.
Yeah, you can hose them down.
Yeah, so you can hose them down, you can clean them down. Yeah, my only concern with using them in the cement application is that we don't want that cement to cake on and dry on there. But if it's in if it has moisture properties already in it and it's in a wet, you know, sort of condition, or in a very dry condition, they would just get knocked out. So I would say that would be an appropriate application. Yeah.
Okay, Nico, I can field the other questions. Okay. So thank you guys. There's another question is for oil mist eliminator. You mentioned that the oil is recovered. So the question is, in oil mist eliminator, what percentage of oil is lost in the filter media?
Actually, you want to take that one, or you want me to go for it, Hank?
Go ahead.
Honestly, majority of the oil is recuperated because it is coalesced. So if my memory serves me right, I think we filtered down the oil mist down to 0.3 micron. So anything smaller than 0.3 may go through, but you know, I'd have to look at our technical documents, but it definitely in excess of 95% of the oil is recuperated. You know, it may be even higher than that, maybe 99-point-something%, but you would be losing very little oil, and that's where the economics come into effect, where we're recuperating that oil. I hope that answers the question.
Zenon, the efficiencies that we have are 99.5 and 99.97 of 0.3 micron.
Okay.
Great.
And
sure.
just if I could elaborate on that one, you know, earlier we were stating that the oil mist can come out at temperatures 350 degrees Fahrenheit, 700 degrees Fahrenheit. Prior to the oil mist, we always want to cool that gas or the air as much as possible to try to bring it as close to ambient temperatures. So some of those oil mists condense, turn back into an aerosol or into a liquid form, and then the oil mist eliminator works more efficiently. So typically we want to get the temperature down in the 120 degree Fahrenheit range. So we may use like an elongated pipe prior to going to the oil mist eliminator to create some cooling prior to the exhaust.
Thank you, guys. Next question is about Coalescer separator. Can your company make two-stage system that's include particulate removal and coalescers in the same vessel? If yes, would these filter media or cartridges be different type, like one for coalescers, one for particulate removal, or they will be the same media will do it?
No, it will be two different cartridges, completely, even different materials, depending on the filtration requirements and the gas. We can use a polypropylene, a polyester, a Nomex, woven glass, matte glass. So that's one. The coalescing media is a completely different media, and it has a completely different function as well, where the filter media works basically as a sieve. The coalescer has the main goal to coalesce the droplets. So no, they're not the same, and you will have to have two different elements.
Okay.
If I can just elaborate on that one too, you know, as Hank was stating, it's two different medias. In theory, coalescing filters, their goal is to remove aerosols, liquid droplets. So if there were no particulates in the gas stream, then that coalescing filter should have an infinite life. In reality, there is always a certain amount of particulates, but if you would have a particulate filter prior to a coalescing filter, and the first stage was removing all the particles, second stage the coalescer, then in theory you should have infinite life on the second stage. Since the particulate filter is outside infiltration, you have more surface area, so it may be more cost effective. But again, you know, that's why we have people like Hank and some of our design engineers to evaluate based on the particulate and the liquid load and all of those factors.
And then the question that I would have is what is the liquid range that the customer is looking for? Because besides just the elements, we can use mash pads, chevrons to knock out a knockout pot to remove the bulk of the liquid. So there's a number of options that we can combine to create a system that removes and particles and liquid.
Thank you. The second part of the question was, would these two type of filters, can they be in the same vessel?
Yes, we can design it where it would fit in one vessel.
Okay, thank you.
Yes.
That takes me to, there's one more last questions. You mentioned about the sump optimization to knock off the moisture and particulate. Can baffle design be also optimized at the inlet to knock off the moisture and particulate?
Yes, you can. You can use a baffle to remove liquid from a gas, but it will never be as efficient as either a chevron, mesh pad, a mash pad, or an element. What we see is that if if we have a liquid with a high liquid load, then we'll use a knockout pot as a first stage, and then a combined gas filter where we have either a chevron or a mash pad and an element as a polishing unit.
Okay. Thank you. Actually, so that was the last question. And to everybody there, you know, Zenon's contact information, or feel free to contact anybody from John Brooks. We have our filtration technical salespeople across Canada. You know, please send the questions. And guys, you want to add anything before we close? Because it's 2 o'clock Eastern Standard Time now.
Well, just want to thank everybody for attending, and you know, stay safe, and you know, please visit our site. There's loads of technical information, other webinars. If you didn't have the chance to watch today's, there's pre-recorded sessions. Also, if you want a certificate of attendance, we can offer that also. Just send us your emails, and we will, you know, gladly reply to them.
Yeah, and thank you. With this, I will sincerely like to thank our guest host, Henk, again. For
Oh, you're welcome.
time.
Thank you for having me.
And you know, the wealth of knowledge and experience that you bring, especially working for a company like Dollinger, which is Celeros now. I know they have the greatest product line there. Thank you again.
You're welcome. Welcome.
Yeah. Okay.
Thank you.
Thank you all.
All right.
Thank you.
Bye.
Yes, bye. There's one, somebody's asking, can we get certificate of attendance? Yes, we will provide the certificate of attendance.
Yes, definitely.